take everything you think you know about solid matter and throw it away. Right now, somewhere in our galaxy, there are objects where a single sugar cube-sized piece of material would weigh about as much as all of humanity combined. Objects where the very atoms that make up your body, the planet beneath you, and the stars overhead have been crushed so completely that they simply cease to exist. Not melted, not shattered, erased as recognizable matter. Inside these collapsed remnants, gravity squeezes so violently that the empty space inside every atom is wrung out entirely. Electrons are rammed backward into protons, and matter is forced across a threshold into states we barely have the physics to describe. What survives down in the core might not be matter as we know it at all. Tonight, we descend into one of these objects, layer by layer, and watch the universe crush matter out of existence. If you find these kinds of deep dives into the strangest corners of physics fascinating, a quick like or subscribe genuinely helps this channel keep going. It's a small thing for you, but it means a lot to me. Now, let's begin. Let's start where the crushing begins, with a star that has run out of time. Imagine a star far more massive than our Sun, perhaps 8, 10, 20 times its mass, blazing away in the dark. For most of its life, this star is locked in a delicate, almost miraculous balance. Deep in its core, hydrogen is being fused into helium, and that fusion releases a torrent of energy, an outward push of radiation and heat and pressure. At the same time, the star's own colossal gravity is trying to crush everything inward toward the center. These two forces, the outward push of fusion and the inward pull of gravity, fight to a standstill, and that standstill is what we call a star. A star is not a still object. It is a war that has reached a temporary stalemate, and that stalemate can last for millions of years. But here is the problem hiding inside every massive star. Fusion needs fuel, and fuel runs out. As the hydrogen in the core is exhausted, the star begins to fuse helium into carbon. When the helium runs low, it fuses carbon into heavier elements still, then neon, then oxygen, then silicon. With each new stage, the star is burning through more exotic, heavier ash, and it is doing so faster and faster. The hydrogen burning phase might last 10 million years. The later stages can last mere centuries, then years, then days. The star is racing toward a wall it cannot see, and that wall is made of iron. Why iron? This is one of the most important facts in all of stellar physics, so let's be precise about it. Fusion releases energy only when you fuse light elements into slightly heavier ones, because the resulting nucleus is more tightly bound and the leftover energy is released. But iron sits at the bottom of a kind of energy valley. Iron is the most tightly bound nucleus there is. You cannot get energy by fusing iron into something heavier. In fact, fusing iron costs energy rather than releasing it. So when a massive star finally builds up a core of iron at its center, that core is dead weight. It cannot fuse, it cannot push back, it produces no outward pressure from fusion at all, and yet the iron core does not immediately collapse, and the reason why is the first key to everything that follows. The core is held up not by fusion but by something far stranger, a purely quantum mechanical effect called electron degeneracy pressure. To understand a neutron star, you have to understand this pressure first, because the whole drama of the neutron star is the story of this pressure failing and being replaced by something more extreme. Here's the idea. Electrons are a type of particle that obey a strict rule discovered by the physicist Wolfgang Pauli, a rule known as the Pauli exclusion principle. In its simplest form, This rule says that no two electrons can occupy exactly the same quantum state at the same time. You can think of quantum states loosely as slots, like seats in a vast cosmic auditorium. Each seat can hold only one electron with a given set of properties. When matter is squeezed, you're trying to force more and more electrons into a smaller and smaller space, which means trying to cram them into fewer available seats. But the seats cannot be shared. As the lower energy seats fill up, electrons are forced to occupy higher and higher energy states, moving faster and faster, whether they want to or not. This creates an outward pressure, a resistance to being squeezed that has nothing to do with temperature or heat. It is a pressure that exists simply because electrons refuse to be packed into the same state. This is degeneracy pressure, and it is astonishingly powerful. This is the same pressure that holds up a white dwarf, the kind of dense stellar corpse our own sun will eventually become. A white dwarf packs roughly the mass of the sun into a sphere about the size of the Earth. In a white dwarf, the atoms have already been partly crushed. The neat structure we learn about in school, with electrons orbiting a nucleus in tidy shells, is gone. Instead, you have bare nuclei sitting in a roiling sea of free electrons, and it is the degeneracy pressure of those electrons that keeps the whole thing from collapsing further. A teaspoon of white dwarf material would weigh several tons here on Earth. That already sounds extreme, but a white dwarf is only the opening act. A neutron star takes this same logic and pushes it to a place that is almost incomprehensible. Now, in the early 1930s, a young physicist named Subramanian Chandrasekhar worked out something that shocked the astronomical community of the time. He calculated that electron degeneracy pressure, mighty as it is, has a hard limit. It cannot hold up an unlimited amount of mass. The reason is subtle and beautiful. As you pile more mass onto a degenerate core, gravity squeezes harder, the electrons are forced into ever higher energy states, and they begin to move at speeds approaching the speed of light. Once the electrons become relativistic, meaning they are moving so fast that the rules of special relativity dominate, something changes about how their pressure responds to compression. The pressure can no longer rise quickly enough to keep pace with the relentless increase in gravity. Beyond a certain mass, the electrons simply cannot push back hard enough, no matter how tightly they are packed. That critical mass is now called the Chandrasekhar limit, and it sits at roughly 1.4 times the mass of the Sun. If a degenerate core stays below that limit, it can hold itself up forever as a white dwarf, slowly cooling over billions of years. But if the core exceeds that limit, electron degeneracy pressure loses the war. There is nothing left to stop gravity. And inside a dying massive star, that iron core just keeps growing as the layers above it dump more and more iron ash down onto it. When the iron core finally tips past the Chandrasekhar limit, the floor gives way. What happens next is one of the most violent events in the universe, and it happens with breathtaking speed. The collapse of the core is not gradual, it is a catastrophe measured in fractions of a second. A core roughly the size of the Earth collapses down toward a sphere only tens of kilometers across in well under a second. The inner core falls inward, at speeds reaching a significant fraction of the speed of light. Temperatures soar into the billions of degrees, and in that instant, gravity begins to do something to matter that gravity almost never gets to do anywhere else in the cosmos. It begins to crush atoms out of existence. Let's slow down and really look at what an atom is, because to appreciate this crushing, You have to appreciate just how flimsy and empty ordinary matter truly is. An atom is mostly nothing. At the center sits the nucleus, made of protons and neutrons, and that nucleus contains nearly all of the atom's mass. But the nucleus is fantastically tiny compared to the atom as a whole. If you blew up an atom until it was the size of a large sports stadium, the nucleus would be about the size of a marble sitting at the very center of the field. Everything else, the entire vast volume of the stadium, is occupied only by the electrons, which are not even solid specks but smeared out clouds of probability, whirring through that enormous emptiness. So when you knock on a table and it feels solid, what you are really feeling is not solid matter at all. You are feeling the electric repulsion between the electron clouds in your hand and the electron clouds in the table. The solidity of the everyday world is an illusion held together by electromagnetism and by the Pauli exclusion principle, keeping those electron clouds apart. Matter is almost entirely empty space, propped open by electrons that refuse to overlap. And that means there's an enormous amount of room to squeeze, if only something could push hard enough to overcome the electrons. In ordinary life, nothing can. The forces involved are simply too great. But the gravity of a collapsing stellar core is not ordinary. It is one of the few forces in the universe strong enough to call that bluff. In the first phase of collapse, gravity strips matter of its atomic identity entirely. Under normal conditions, even in something as dense as the center of the sun, atoms retain some semblance of structure. But as the core density climbs, the atoms are pressed so tightly together that their electron clouds can no longer remain bound to individual nuclei. The electrons are torn loose and merge into a common sea, a uniform ocean of free electrons in which bare atomic nuclei float like islands. At this stage, we no longer have atoms in any meaningful sense. We have a plasma of nuclei and electrons crushed into a fraction of the volume the atoms once occupied. This is the same fundamental state as a white dwarf interior, but inside the collapsing core, it is only a way station, a brief moment on the road to something far stranger. This is the first threshold, and it is worth pausing on because it is exactly the kind of moment the title of this story promises. The mostly empty atom, that flimsy stadium with a marble at the center, can no longer survive. The empty space that defines ordinary matter is being wrung out. The electrons that held the whole structure apart have been pried loose and pulled together. Already, the matter inside this collapsing core bears no resemblance to anything you could hold in your hand, anything you have ever seen, anything that exists naturally anywhere on Earth or in the atmosphere of any ordinary star. And we have barely begun. Now, you might think that once the atoms are gone and the electrons are pulled into a sea, the electron degeneracy pressure would at least slow the collapse, the way it holds up a white dwarf. And in a sense, it tries. But remember Chandrasekhar's insight. We are past the limit. The electrons are being forced to relativistic speeds, and their pressure simply cannot rise fast enough to match the gravity bearing down on them. The collapse continues, and as it does, the density climbs to levels that begin to threaten the integrity of the nuclei themselves. We are approaching the conditions where the very particles inside the nucleus will be rearranged. That is the subject we will descend into next. But before we get there, we need to understand what this collapse unleashes on the rest of the star. Because the collapse of the core is also the trigger for one of the most spectacular explosions in nature. As the inner core plunges inward and reaches nuclear densities, something abrupt happens. The matter at the very center suddenly becomes incredibly stiff, far stiffer than anything that came before, for reasons we will come to shortly. The infalling inner core slams into this newly rigid heart and rebounds, like a hammer striking an anvil and bouncing back. This rebound launches a shockwave outward through the still collapsing outer layers of the star. At the same time, the conversion of matter happening in the core releases an almost unimaginable flood of tiny, nearly massless particles called neutrinos. The numbers here are staggering. In the span of a few seconds, a collapsing stellar core releases more energy in neutrinos than our sun will emit in light over its entire 10 billion year lifetime. Most of that energy pours out invisibly, but a fraction of it gets caught by the outer layers and helps drive them outward. The result is a supernova. The outer layers of the star, everything above the collapsing core, are blasted into space at thousands of kilometers per second. For a few weeks, this single dying star can outshine an entire galaxy of hundreds of billions of stars. The elements forged in the star's long life, and new elements created in the violence of the explosion itself, are scattered across interstellar space, eventually to be recycled into new stars, new planets, and perhaps new life. The calcium in your bones, the iron in your blood, were forged in stars and dispersed by explosions like this. But while all that drama is unfolding in the visible explosion outside, the real story for us is what is left behind at the very center, in the crushed heart that triggered the whole event. Because that core does not blow apart, it stays, and what it becomes is a neutron star. And here is the remarkable thing. We have actually caught one of these collapses in the act, and caught it through those very neutrinos. In 1987, light reached Earth from a supernova in the Large Magellanic Cloud, a small companion galaxy to our own, around 160,000 light-years away. We call that event Supernova 1987A, and it was the closest supernova observed in nearly 400 years, since the one Johannes Kepler watched in 1604. But the truly extraordinary part happened hours before any telescope saw the star brighten. Deep underground, in detectors built inside mountains and mines, instruments designed to watch for these ghostly particles registered a brief burst of neutrinos. The Kamiokande detector in Japan and others around the world recorded just a couple of dozen neutrino events over the span of about 13 seconds. 24 particles out of a flood so immense that an unimaginable number passed harmlessly through every human body on the planet in that instant without anyone feeling a thing. Those few captured particles were the direct exhaust of a stellar core collapsing and neutronizing, the literal signature of atoms being crushed into neutrons, arriving at Earth after a journey of 160,000 years. The neutrinos arrive before the light, precisely because they streamed straight out of the collapsing core at nearly the speed of light, while the light had to wait hours for the shockwave to reach the star's surface and make it flare. It was the first time humanity had ever detected a star dying from the inside, a confirmation written in particles that everything we have just described about the collapse is not merely theory, but something that actually unfolds in the real universe. Let's get a feel for the scale of the object we are talking about, because the numbers are so extreme they are almost comical. A neutron star packs somewhere between about 1.5 and 2 times the mass of our entire sun into a sphere roughly 20 kilometers across. 20 kilometers. That is the size of a modest city. You could drive across a neutron star if it did not instantly vaporize and crush you in the time it takes to cross a major metropolitan area. And into that city-sized ball is packed more mass than the entire sun. A sun that is well over 1 million kilometers across and could swallow more than 1 million Earths. To translate that into something graspable, consider the density. A single sugar cube-sized piece of neutron star material, a cubic centimeter, would have a mass of roughly 100 million tons here on Earth. Some estimates push that figure toward 1 billion tons for the densest regions. Think about that. A volume you could balance on your fingertip would weigh as much as a mountain, as much as a significant fraction of all the human beings who have ever lived, stacked together. The density inside a neutron star is comparable to the density of an atomic nucleus itself. And that is the deep secret of what a neutron star really is. In a sense, a neutron star is what you would get if you took an atomic nucleus and scaled it up to the size of a city. It is matter-packed at nuclear density, but instead of being confined to a microscopic nucleus held together by the strong nuclear force, it is held together on a colossal scale by gravity. The surface gravity of such an object defies intuition. If you could somehow stand on the surface of a neutron star, the gravitational pull would be on the order of 100 billion times stronger than what you feel standing on Earth. An object dropped from a height of 1 meter would hit the surface in a tiny fraction of a second, having accelerated to a speed of millions of kilometers per hour. You yourself would not survive the approach. The tidal forces, the difference in gravity between your head and your feet, would stretch and shred you into a thin stream of atoms long before you arrived. And then those atoms would suffer the same fate that the original star's matter suffered. They would be crushed, ionized, and ultimately fed into the same crushing process we have been describing. Their structure annihilated as surely as everything else that falls onto such an object. There is another property worth introducing here, because it helps explain how we even know these objects exist. When the iron core collapses, two things are dramatically amplified. The first is rotation. The original core was spinning slowly, but as it shrinks down to a tiny fraction of its former size, it spins faster and faster, the same way a figure skater spins faster when they pull in their arms. A newborn neutron star can rotate many times per second, and some, called millisecond pulsars, rotate hundreds of times every single second, their entire surface whipping around at a sizable fraction of the speed of light. The second thing amplified is the magnetic field. As the core collapses, its magnetic field lines are squeezed together, concentrating the field to staggering strengths. Neutron stars possess the strongest magnetic fields known anywhere in the universe, trillions of times stronger than the Earth's. And the most extreme of them, called magnetars, have fields so intense they would scramble the very chemistry of your body from thousands of kilometers away. These two properties combine to make neutron stars visible across vast cosmic distances. A spinning, strongly magnetized neutron star beams radiation out from its magnetic poles. If those poles happen to sweep across the line of sight to Earth as the star rotates, we detect a regular pulse of radiation, a cosmic lighthouse flashing with astonishing precision. These are the famous pulsars, first detected in the late 1960s as a series of impossibly regular radio pulses that were briefly, half-jokingly considered as a possible signal from an alien civilization, before astronomers realized they were the heartbeat of a collapsed star. The regularity of these pulses is extraordinary. Some neutron stars keep time more accurately than the best atomic clocks on Earth. which is one of the ways we have been able to study them so precisely despite their unimaginable distance and tiny size. So we have established what these objects are and how they form, but I want to keep our focus exactly where the title points us, on the matter itself and what is happening to it. Because everything we have described, the city-size size, the nuclear density, the crushing gravity, all of it is a consequence of one central fact. Inside a neutron star, ordinary matter has been compressed across a physical threshold from which there is no easy return. The atoms are gone, the empty space is gone, and as we will see, even the distinction between different kinds of particles begins to dissolve. Let me make this concrete with a comparison that often helps. Picture the matter in your own body right now. It is built from atoms, and those atoms are, as we said, almost entirely empty space. Suppose you could remove that empty space entirely, collapsing every atom so that the nuclei sat directly against one another with no gap. How much would you shrink? The answer is shocking. The entire human race, all 8 billion of us, with all that empty atomic space squeezed out, would fit into a volume smaller than a sugar cube. That is not a metaphor or an exaggeration. It is a direct consequence of how empty atoms are. And that sugar cube of compressed humanity is, more or less, a tiny sample of neutron star matter. The neutron star has simply done to an entire collapsing stellar core what we just imagined doing to the human race. It has removed the emptiness. This is the sense in which atoms are crushed out of existence. Not that the underlying particles are destroyed, at least not yet, but that everything we associate with an atom, the structure, the electron shells, the chemistry, the vast internal emptiness, has been obliterated. You could not do chemistry inside a neutron star. The concept does not apply. There are no molecules, no elements in the ordinary sense, no compounds, none of the architecture that the entire science of chemistry is built upon. All of that requires atoms with intact electron clouds, and there are no such atoms here. The matter has been pushed into a regime where the rules that govern everything in your everyday experience simply no longer hold. And we should be honest about the threshold itself, because it is not a single sharp line, but a series of them, each one marking the failure of some structure that ordinary matter relies on. We have just crossed the first one, the point where the electron clouds can no longer remain bound to nuclei, where atoms dissolve into a plasma of bare nuclei and free electrons. That threshold is crossed in the outermost regions, where the density is merely thousands of times that of water. As we go deeper, the density climbs by factors of millions and then billions, and at each new level of compression, matter is forced to abandon another structure, to surrender another piece of its familiar identity. The deeper you go, the less the matter resembles anything you have a name for. It is worth dwelling for a moment on just how alien this makes a neutron star, even at this first stage of our understanding. We've explored, in our imaginations and with our instruments, planets and moons and comets, the surfaces of distant worlds, the interiors of gas giants, the blazing cores of ordinary stars. All of those, however exotic, are made of atoms. They are made of the same fundamental building blocks as you and I, arranged in different ways under different conditions, but recognizably the same kind of stuff. A neutron star is the first object in our journey that is genuinely made of something else. Cross its surface and you leave the entire domain of atomic matter behind. You enter a regime that exists nowhere on Earth, that cannot be created in any laboratory we have ever built, and that can only be studied through a combination of distant observation and the hardest theoretical physics we possess. That, in fact, is one of the most remarkable things about neutron stars from a scientific point of view. They are natural laboratories for physics at densities we can never hope to reproduce on Earth. The most powerful particle accelerators we have built can momentarily create tiny, fleeting flecks of ultra-dense matter, but nothing remotely like the sustained, bulk, city-sized lump of nuclear density material that a neutron star represents. So when physicists want to understand how matter behaves when it is squeezed beyond all earthly limits, they look to neutron stars. The questions of what happens to matter under such crushing pressure, the questions this whole story is built around, are not merely curiosities. They sit at the frontier of fundamental physics, where our theories of the very small, the physics of nuclei and particles, must meet our theories of the very large, the physics of gravity and collapsed stars. So here is where we stand at the end of this first stage of our descent. A massive star has died. Its iron core, unable to fuse and unable to hold itself up once across the Chandrasekhar limit, has collapsed in a fraction of a second. The collapse stripped matter of its atomic structure, prying electrons loose from nuclei and pooling them into a degenerate sea. Electron degeneracy pressure, the quantum stubbornness of electrons refusing to share quantum states, tried to halt the fall but was overwhelmed. The collapse triggered a supernova that lit up the sky and seeded the galaxy with heavy elements, and left behind at the center is a city-sized ball of matter compressed to the density of an atomic nucleus, spinning rapidly, blazing with magnetism, and made of something that is no longer ordinary matter at all. But notice what we have not yet explained. We called it a neutron star, and yet so far our story has been about electrons and nuclei, not neutrons. Where do all those neutrons come from? The star did not start out made of neutrons. It started out, like all stars, mostly made of hydrogen, which is to say protons and electrons. Somewhere in this crushing process, vast numbers of protons and electrons must have been transformed into neutrons. And that transformation is the second great threshold of our descent. The moment when gravity reaches past the structure of the atom and begins to rewrite the particles themselves. It is a process where the electron, that stubborn particle whose pressure we have leaned on so heavily, is finally forced into the proton, and matter is remade at the most fundamental level we have yet encountered. That is where we turn next. As we follow the matter deeper, watching it shed one more layer of its familiar identity, and become the neutron-rich substance that gives these extraordinary objects their name. We left off with a puzzle. We have been describing the collapse of a stellar core in terms of nuclei and electrons. The same ingredients that make up a white dwarf, yet the object we are building is called a neutron star, an object overwhelmingly made of neutrons. So somewhere in this story, an enormous transformation has to take place. Vast oceans of protons and electrons must somehow become neutrons. To understand how that happens is to understand the single most defining event in the life of this matter, the moment that gives a neutron star its very name. And it begins, fittingly, with the failure of the electrons we have leaned on so heavily. Let's return to those electrons, pooled into a dense, degenerate sea, packed shoulder to shoulder in defiance of the Pauli exclusion principle. Remember what that principle forces upon them. No two electrons can occupy the same quantum state. So as they are squeezed into less and less volume, They are forced to climb into higher and higher energy levels. They move faster and faster, not because anything has heated them, but simply because there is nowhere lower left to go. Every low energy seat is taken, so each additional electron has no choice but to take a higher, faster seat. As the collapse continues and the density soars, the electrons at the top of this energy ladder are moving at speeds extremely close to the speed of light, and they carry truly enormous energies. This is the relativistic regime that Chandrasekhar identified, and it turns out to be the doorway to something remarkable. Here is the key. When you give electrons that much energy, you open up a reaction that, under normal conditions, essentially never happens. Ordinarily, a proton and an electron can coexist quite happily side by side. They attract one another electrically, but they remain distinct particles. The proton is positively charged, the electron negatively charged, and that is simply how matter is arranged. But there exists a process by which a proton can absorb an electron and become a neutron, emitting a tiny, nearly massless particle called a neutrino in the bargain. This process is called electron capture, or in the language of nuclear physics, inverse beta decay. The reason it does not happen in ordinary matter is that a neutron is slightly heavier than a proton and electron combined. Nature does not usually let you spontaneously make something heavier out of something lighter because that costs energy, and energy must be supplied from somewhere. But in the crushing interior of a collapsing core, that energy is exactly what the relativistic electrons have in abundance. Those ultra-energetic electrons at the top of the degenerate sea carry more than enough energy to bridge the small mass gap. And so, when the density climbs high enough, it becomes energetically favorable, even inevitable, for electrons to be captured by protons. A high-energy electron slams into a proton, the two merge, and out comes a neutron and a neutrino. The neutrino, being almost incapable of interacting with anything, streams away at nearly the speed of light, carrying energy out of the core. The neutron stays behind. This is the process called neutronization, and I want you to appreciate just how strange and profound it is. We are not talking about atoms rearranging, or electrons being knocked off, or nuclei being squeezed together. We are talking about the fundamental particles of matter being transmuted, one type into another. Protons and electrons, the two charged building blocks of all ordinary matter, are being fused and converted into neutral neutrons. The electric charge that defines so much of how matter behaves, that gives rise to all of chemistry, all of electromagnetism, all the forces that make solid objects solid, is being systematically erased. Positive proton plus negative electron becomes neutral neutron. The matter is, quite literally, being neutralized. Think about what this means for the electrons specifically. Throughout this entire story, the electrons have been the heroes holding back gravity. Their refusal to share quantum states, their degeneracy pressure, was the only thing standing between the core and total collapse. And now, gravity has found a way to remove them entirely. Every time an electron is captured by a proton, it vanishes from the degenerate sea. It is gone, swallowed into a neutron. And here is the cruel feedback at the heart of the collapse. The more electrons are captured, the fewer electrons remain to provide degeneracy pressure. The less pressure there is, the less resistance gravity meets, so the core collapses faster. The faster it collapses, the higher the density climbs, and the higher the density, the more electron capture is favored. It is a runaway process. Neutronization does not just accompany the collapse, it accelerates it. The very particles that were holding the core up are being consumed by the conditions their own compression created. This is why the collapse of a stellar core is so sudden and so total. It is not a gentle settling. It is a cascade in which the support structure devours itself. In a fraction of a second, an enormous fraction of the protons and electrons in the inner core are converted into neutrons. The matter that began as a plasma of nuclei and electrons is transformed into something dominated by neutrons. And as it happens, that flood of neutrinos we mentioned earlier comes pouring out. Each electron capture releases a neutrino, and with so many captures happening so quickly, the core radiates an almost unfathomable number of these particles. This is the source of the staggering neutrino luminosity, the burst that briefly carries more power than a galaxy. The neutronization of the core is, in a very real sense, the engine of the supernova, and the neutrinos are its exhaust. Now, let's slow down and follow this transformation more carefully as it unfolds across increasing density, because it does not happen all at once or uniformly. It proceeds in stages, and each stage represents a further departure from the matter we know. To do this, we need to think about what happens not to isolated free protons, but to the protons bound inside atomic nuclei, because in the outer parts of this matter, the protons are not free. They are locked inside nuclei, and those nuclei have their own response to the crushing. Consider a nucleus, a cluster of protons and neutrons bound together by the strong nuclear force. In ordinary matter on Earth, nuclei have a fairly balanced mix of protons and neutrons. Light elements tend to have roughly equal numbers of each. Heavier elements carry somewhat more neutrons than protons, but the imbalance is modest. There is a reason for this balance. Protons repel one another electrically, since they all carry positive charge, so a nucleus with too many protons becomes unstable. But neutrons are not free to add without limit either, because of, once again, the Pauli exclusion principle, which applies to neutrons just as it does to electrons. There is an energetic cost to making a nucleus too lopsided in either direction. Nature settles on a balance that minimizes the total energy, and that balance is what gives us the familiar isotopes of the elements. But inside the crushing matter of a collapsing core or a newborn neutron star, that balance is forced to shift dramatically. As the density climbs and the surrounding electrons become more and more energetic, those electrons begin to be captured by the protons inside the nuclei themselves. A proton inside a nucleus absorbs a high-energy electron and turns into a neutron, right there within the nucleus. The nucleus does not break apart. It simply becomes more neutron-rich. Then, it happens again. And again. The nuclei in this environment grow more and more lopsided, accumulating neutrons and shedding the positive charge of their protons. They become isotopes so neutron-heavy that they could never exist on Earth. Isotopes that would fall apart in tiny fractions of a second under ordinary conditions, but which are held stable here by the extraordinary pressure of the surrounding matter. This is a beautiful and subtle point that deserves emphasis. On Earth, an absurdly neutron-rich nucleus is unstable. It would immediately undergo the reverse process, called beta decay, in which one of its excess neutrons converts back into a proton, spitting out an electron to rebalance the charge. That is how nature normally corrects an overabundance of neutrons. But inside this crushed matter, that escape route is blocked. Why? Because beta decay would produce an electron, and the electron would need somewhere to go. It would need an available quantum state to occupy. But the sea of electrons around the nucleus is already degenerate, already packed full, with every low-energy state taken. There is no empty seat for the new electron. The Pauli exclusion principle forbids it from being created with nowhere to go. So the decay is suppressed. The nucleus is trapped in its neutron-rich state, unable to shed its excess neutrons because the universe around it has run out of room for the electrons that decay would produce. Step back and take in what is happening here, because it is the second great threshold of our descent. Every bit as significant as the destruction of atoms we described earlier. In the first threshold, gravity crushed the electron clouds and dissolved the atom, leaving bare nuclei in a sea of electrons. Now, in this second threshold, gravity reaches inside the nuclei and begins rewriting their very composition, transmuting their protons into neutrons, driving them into configurations that have no counterpart anywhere in the natural world we know. The matter is no longer made of ordinary elements at all. It is made of bloated, neutron-saturated nuclei that exist only under these conditions, suspended in a thinning sea of the electrons that have not yet been captured. We have moved from the destruction of atomic structure to the rewriting of nuclear structure. Gravity is digging deeper into the architecture of matter, dismantling it one level at a time. As we descend further and the density continues its relentless climb, we reach a threshold with a wonderfully evocative name. It is called neutron drip. To understand it, picture those nuclei, now grotesquely overloaded with neutrons, packed ever more tightly together. There comes a density at which the nuclei simply cannot hold any more neutrons. They are so saturated that adding even one more neutron is no longer energetically favorable. The neutron would rather be outside the nucleus than inside it. And so, at this critical density, neutrons begin to leak out of the nuclei entirely. They drip free, like water squeezed from a saturated sponge. This is the neutron drip point, and it marks yet another fundamental transition in the nature of the matter. Below the neutron drip density, all the neutrons are locked inside nuclei. Above it, something new appears. Free neutrons, no longer bound to any nucleus, beginning to fill the spaces between the nuclei. We now have a three-component mixture. We have the neutron-rich nuclei themselves, we have the thinning sea of free electrons, and now we have a growing ocean of free neutrons surrounding everything. As the density climbs higher and higher above the drip point, more and more neutrons leak out. The free neutron ocean grows, and the nuclei become a smaller and smaller fraction of the total. The matter is transitioning from being mostly nuclei with a few free neutrons, to being mostly free neutrons with a few residual nuclei dissolved within them. And this is the moment to introduce the new force that will hold the star up. Because by now you should be wondering, with the electrons being captured and converted, what is left to resist gravity? We saw that electron degeneracy pressure failed past the Chandrasekhar limit. We saw the electrons being consumed by neutronization. So why does the neutron star not simply continue collapsing all the way down to a black hole? The answer is that the neutrons themselves come to the rescue, and they do so using the very same trick the electrons used, the Pauli exclusion principle, but on a far more powerful scale. Neutrons, like electrons, are particles that obey the exclusion principle. No two neutrons can occupy the same quantum state. So as the free neutrons are packed into an ever denser ocean, they too are forced to climb into higher and higher energy levels, and they too generate a degeneracy pressure that resists further compression. This is neutron degeneracy pressure, and it becomes the new pillar holding the star against gravity. But here is why it is so much more effective than electron degeneracy pressure at these extreme densities. Neutrons are nearly 2,000 times more massive than electrons. The way degeneracy pressure works, more massive particles can be packed to far higher densities before they are forced to relativistic speeds. So neutron degeneracy pressure can hold up against the crushing weight of more than a solar mass of material compressed into a city-sized sphere. Conditions that would have crushed an electron-supported object long ago. The neutrons step in precisely where the electrons gave out, and they hold the line at a density 1 billion times greater than anything the electrons could have managed. This is the deepest sense in which a neutron star earns its name. It is an object held up against its own colossal gravity, not by fusion, not by thermal pressure, not by electrons, but by the sheer quantum stubbornness of neutrons refusing to share their quantum states. The entire structure, this city-sized ball with the mass of the sun, is balanced on the exclusion principle applied to neutrons. It is one of the most extraordinary facts in physics that an abstract quantum rule about which states particles are allowed to occupy is the only thing standing between such an object and total gravitational collapse. And here is something worth marveling at. This entire object, so utterly removed from anything in human experience, was dreamed up on paper before anyone had ever seen one. In 1932, the neutron itself was discovered in a laboratory, finally identified as a distinct particle. And just 2 years later, in 1934, two astronomers, Walter Baade and Fritz Zwicky, made one of the boldest leaps in the history of science. They proposed that when a massive star exhausts itself and explodes, what they were the first to call a supernova, the collapse could leave behind a star composed almost entirely of neutrons, packed together at the density of a nucleus. Bear in mind, the neutron was barely understood. No one had any direct evidence such an object could exist, and it would be more than 3 decades before the first pulsar was detected and the prediction confirmed. Yet they reasoned their way to it from the bare logic of the physics, the same logic we have been following. It stands as a stunning demonstration that the human mind, armed with the right principles, can foresee the existence of objects so extreme that the entire vocabulary of ordinary matter breaks down in describing them. I want to make sure the strangeness of the resulting material is fully clear, because it is genuinely outside the bounds of ordinary categories. What we now have in the bulk of this matter is an ocean of free neutrons at nuclear density. Imagine that. Free neutrons, normally found only fleetingly inside nuclei or in the brief moments after they are knocked loose in a reactor, here existing in bulk by the trillions upon trillions of trillions, packed together to form the substance of an entire star. On Earth, a free neutron is an unstable, ephemeral thing. Pluck a neutron out of a nucleus and leave it alone, and within about 15 minutes, on average, it will decay. It will fall apart into a proton, an electron, and an antineutrino, because, as we noted, a neutron is slightly heavier than a proton and electron combined, and nature prefers to roll downhill toward lower energy. So how can a neutron star be made of free neutrons that persist for millions or billions of years, when a free neutron on Earth survives only minutes? The answer is the same logic we encountered before, the Pauli exclusion principle slamming a door shut. For a neutron to decay, it must produce a proton and an electron, And both of those particles need available quantum states to occupy. But in neutron star matter, the few protons and the few electrons that exist are also degenerate, also packed into a sea with every low energy state already filled. A decaying neutron would try to create a proton and an electron, but there is nowhere to put them. The states are full. The decay is forbidden, blocked by the exclusion principle. And so the neutrons, which would be unstable in isolation, are rendered stable in bulk by the very crowding that defines the neutron star. The matter is stabilized by its own extremity. Remove a single neutron and set it free, and it would decay in minutes. Pack a sun's worth of them together, and they endure for the age of the universe. This is a profound inversion of our intuitions about matter. We think of free neutrons as fragile and fleeting, and we think of ordinary atoms as stable and enduring. Inside a neutron star, the situation is exactly reversed. The atoms cannot exist at all. They were crushed out of existence long ago. The free neutrons, fragile elsewhere, are here the stable, dominant, enduring form of matter. Everything we know about which kinds of matter are robust and which are delicate has been turned inside out by the crushing pressure. This is what it means to push matter across a threshold into a new regime. It is not merely that things get denser. It is that the rules about what can exist, and what is stable, and what matter even is, are rewritten from the ground up. It is worth pausing to consider just how little of this matter is anything other than neutrons. In the deep interior, calculations suggest that the matter is something like 90% or more neutrons, with only a small residual fraction of protons and an equally small fraction of electrons mixed in. That small fraction is not incidental though. It plays an important role. The protons and electrons that remain are there because of a delicate balance. If you convert absolutely every proton and electron into neutrons, you would actually raise the total energy of the system because of how the exclusion principle costs energy for the neutrons. Nature finds the lowest energy configuration, which turns out to be overwhelmingly neutrons, but with a small, stable admixture of protons and electrons that keeps the whole system in balance. This balance between neutrons on one side and protons plus electrons on the other is governed by the same inverse beta decay and beta decay processes we have been discussing, now reaching a kind of equilibrium. It is a frozen truce between the forces that want to convert protons to neutrons and the forces that want to convert them back, settling at a ratio dictated by the density and the exclusion principle. Let me also address something that might be nagging at you. We have talked a great deal about the exclusion principle as though it were a kind of magic that holds everything up and forbids decays. It is worth being clear that this is not hand-waving. It is among the most rigorously tested principles in all of physics. The exclusion principle is what gives atoms their structure, what makes the periodic table of elements have the shape it does, what keeps the electrons in your own body from collapsing into the nuclei. Every solid object you have ever touched owes its very solidity to this principle, keeping particles out of each other's states. Inside a neutron star, the same principle that gives a tabletop its firmness is operating on a stupendous scale, holding up an entire collapsed star and dictating which nuclear transmutations are permitted and which are forbidden. It is the same rule, just pushed to a cosmic extreme. There is a deep unity here. The quantum law that organizes the gentlest matter in your hand is the same law that governs the most violent, crushed matter in the universe. So let's take stock of where the matter stands now, having crossed the second great threshold. We began this stage with a sea of nuclei and relativistic electrons. The electrons, energized by compression, were captured by protons, transmuting them into neutrons and releasing a flood of neutrinos. This neutronization stripped the matter of its electric charge and consumed the electrons that had been holding gravity at bay, accelerating the collapse. The nuclei that remained grew grotesquely neutron-rich, locked into configurations impossible on Earth, unable to decay because the exclusion principle left no room for the electrons that decay would produce. Then, at the neutron drip threshold, neutrons began to leak free of the nuclei entirely, filling the spaces between them with a growing ocean of free neutrons. And finally, those free neutrons, through their own degeneracy pressure, took over the job of holding the star up, providing a far more powerful resistance than the electrons ever could. The matter has been remade at the level of its fundamental particles. It is now a substance dominated by free neutrons, stabilized by its own crushing density, obeying rules that invert everything we thought we knew about which matter is fragile and which endures. And yet, even now, we have only described the matter in broad strokes, as if it were uniform throughout. It is not. A neutron star is not a featureless ball of identical neutron soup. It has structure, layers, a rich and bizarre internal geography that changes as you descend from the surface toward the center. The transformations we have described do not all happen in the same place. They happen at different depths, at different densities, creating distinct regions stacked one atop another, like the layers of some impossible planet. There is a surface and an atmosphere, thin and strange. There is a solid crust, crystalline and rigid beyond imagining. There is a transitional zone where the matter contorts itself into shapes that physicists have named after pasta, because no other vocabulary quite captures their forms. And beneath all of that lies the core, the deep interior where the densities climb beyond even what we have so far described, into a realm where our confident knowledge begins to fade and the truly exotic possibilities emerge. We have transformed the matter, now we must descend through it, layer by layer, and map the strange architecture that this crushing has built. That descent is where we turn next. So far, we have talked about neutron star matter as though it were one substance, transformed all at once. But the truth is far richer and far stranger than that. A neutron star is not a uniform ball of neutron soup. It is a layered world, an object with a definite geography, where the matter changes its character profoundly as you descend from the surface toward the center. Each layer is defined by the density at that depth, and since the density climbs by a factor of many millions as you go from the surface to the core, each layer represents matter in a wholly different state. If we could somehow drill a shaft from the surface to the center and ride down it, we would pass through a sequence of environments more alien than anything in science fiction, each one a different answer to the question of what matter does when it is crushed. Let's make that descent now, slowly, layer by layer. We begin at the very top, with something that might surprise you. A neutron star has an atmosphere. It is nothing like the atmosphere of a planet, of course. It is fantastically thin, perhaps only a few centimeters thick in many cases, sometimes less than the height of a coin standing on edge. And it is made not of air, but of an extremely hot, fully ionized plasma. The lightest elements that happen to be present, mostly hydrogen or helium, left over from material that has fallen onto the star or been left behind by the explosion. This wisp of an atmosphere is crushed against the surface by that staggering surface gravity we described, the gravity 100 billion times stronger than Earth's. Despite being so thin, this atmosphere matters enormously to astronomers, because it is the layer that shapes the radiation we actually detect. The light that escapes a neutron star and crosses the galaxy to reach our telescopes is filtered through this paper-thin shell of plasma, and by studying that light, we can begin to infer the temperature and properties of the surface beneath. Before we go further down, it is worth pausing on the question we glossed over earlier. How exactly does a neutron star produce those famous pulsars? The lighthouse beam that lets us find it at all? The answer lives in the region just above the surface, in what is called the magnetosphere, and it is a beautiful piece of physics. The star's magnetic field is so colossal, and the star is spinning so fast, that the two together act like a gigantic electrical generator. A spinning magnetic field generates enormous electric fields so strong they can rip charged particles right off the surface and fling them outward along the magnetic field lines. Those particles, accelerated to nearly the speed of light, pour out from the magnetic poles and radiate beams of energy as they go. Here is the crucial detail. A star's magnetic poles do not have to line up with its spin axis. On Earth, the magnetic North Pole is offset from the geographic North Pole, and the same is true, often far more dramatically, on a neutron star. So as the star rotates, the magnetic poles, and the beams streaming out of them, swing around like the beam of a lighthouse, mounted at an angle. If one of those beams happens to sweep across the Earth, we see a flash. Then the star rotates, the beam swings away, and we see darkness. Then it comes around again, and we see another flash. The pulse we detect is not the star turning on and off. It is the star turning, its steady beam crossing our line of sight once or twice per rotation. This is why the timing is so extraordinarily regular, because it is governed by the rotation of a colossal, rigid object, and why a sudden change in that timing tells us something has happened inside. Below the atmosphere lies the surface itself, and then, almost immediately, the outer crust. And here we encounter the first solid layer, though calling it solid hardly does it justice. The outer crust is a crystalline lattice, a rigid, ordered arrangement of atomic nuclei locked into place, surrounded by that sea of free electrons we discussed earlier. In the uppermost regions of the crust, the nuclei are familiar ones, mostly iron, the same iron that formed the dead core of the original star. The electrons flow freely between them, much as electrons flow through a metal here on Earth, which means that in a sense the outer crust behaves like a colossal, perfect metal. But the comparison breaks down quickly when you consider the strength of this material. The crust of a neutron star is held together not by ordinary chemical bonds, but by the immense pressure and the electrical forces between the packed nuclei, and it is estimated to be billions of times stronger than steel. It is very likely the strongest material in the entire universe, a crystalline shell so rigid that it can support mountains, though the mountains it supports would be extraordinary in their own right. Let's dwell on those mountains for a moment, because they capture just how strange this layer is. Given the unimaginable gravity, anything we would recognize as a mountain cannot exist. The gravity is so strong that it flattens everything toward perfect smoothness. A neutron star is one of the most perfectly spherical objects in the universe. Its surface is smoothed by gravity to a degree no planet could ever achieve. The tallest possible mountain on a neutron star, the largest deviation its incredibly strong crust could support against that crushing gravity, might be only a few millimeters high, perhaps a few centimeters at the very most. Imagine that, a mountain as tall as the thickness of a few sheets of paper, and yet, because the strength of the crust and the density of the material, such a tiny bump would represent an enormous mass and an enormous stress on the crystalline structure holding it up. The very geography of this world operates on scales that defy every intuition we carry from our own planet. As we descend deeper into the crust, the density climbs, and we cross a threshold we discussed in detail earlier, the neutron drip point. Above this density, all the neutrons were bound inside nuclei. Below it, neutrons begin to leak free. So as we pass from the outer crust into what is called the inner crust, the environment changes. We now have the crystalline lattice of neutron-rich nuclei, still locked in their rigid array, but now they are bathed not only in a sea of electrons, but also in a sea of free neutrons that have dripped out of the nuclei and flow between them. The inner crust is therefore a strange hybrid, a solid lattice of nuclei suspended in a fluid of free neutrons, with electrons permeating everything. It is simultaneously a solid and a liquid, the lattice rigid while the neutron fluid flows through it. And this dual nature will turn out to have remarkable consequences when we consider how the neutron fluid behaves. But before we reach those consequences, we must pass through one of the most extraordinary regions in the entire object, a transitional zone near the bottom of the inner crust, where matter contorts itself into shapes so peculiar that physicists, reaching for some vocabulary to describe them, settled on the language of Italian food. This is the region of nuclear pasta, and it is one of my favorite subjects in all of physics, because it shows so vividly how matter under crushing pressure abandons the familiar and improvises entirely new forms. To understand nuclear pasta, we have to think about the competition of forces at this depth. The nuclei in the lattice are clusters of protons and neutrons held together by the strong nuclear force, which wants to pull them into compact, roughly spherical blobs, the shape that minimizes their surface area. That is why nuclei are normally little round clusters. The strong force, acting like a kind of surface tension, pulls them into balls. But the protons in those nuclei all carry positive charge, and like charges repel. The electrical repulsion between protons wants to spread the nuclei out, to push them apart. Under ordinary conditions, the nuclei are far enough apart that this is not an issue. Each nucleus is a tidy ball, and the electrical repulsion just keeps the balls separated. But at the bottom of the inner crust, the nuclei are squeezed so close together, occupying such a large fraction of the available space, that these two forces, the strong force pulling matter into compact shapes and the electrical force pushing it apart, come into direct and dramatic conflict. And the resolution of that conflict is the formation of pasta. Here is what happens as the density rises through this zone. At first, the nuclei remain roughly spherical, little round blobs of nuclear matter, and physicists have whimsically named this phase after gnocchi, the small round dumplings. But as the density increases and the blobs are pressed closer, it becomes energetically favorable for them to merge along one direction, fusing into long cylinders, tubes of nuclear matter stretching through the surrounding neutron fluid. This phase is named spaghetti, for obvious reasons. The matter has organized itself into long strands. Push the density higher still, and the cylinders merge sideways into flat sheets, broad plates of nuclear matter stacked with layers of neutron fluid between them, and this phase is called lasagna. The matter has gone from blobs to strands to sheets, reorganizing its very geometry to balance the competing demands of the strong force and the electrical force, and it does not stop there. As the density continues to climb, the arrangement inverts itself. Instead of sheets of nuclear matter separated by fluid, we get sheets of fluid separated by nuclear matter, an inside-out version sometimes called anti-lasagna. Then we find tubes of empty fluid, holes punched through a background of nuclear matter, the inverse of the spaghetti phase, sometimes called anti-spaghetti, or, charmingly, a kind of nuclear Swiss cheese, with the holes being the neutron fluid and the cheese being the nuclear matter. And finally, near the very bottom of this transitional zone, we get bubbles of fluid suspended in nearly continuous nuclear matter, the inverse of the Gnocchi phase, before the matter finally becomes essentially uniform and we pass out of the crust entirely and into the core. The whole sequence, from blobs to tubes to sheets and then their inversions, represents matter exploring every geometric trick available to it as it tries to minimize its energy under crushing compression. I find this genuinely beautiful, and I want to make sure its significance lands. We are accustomed to thinking that matter comes in a few familiar states: solid, liquid, gas, perhaps plasma. Here, under the crushing pressure of a neutron star's crust, matter has invented forms that belong to none of those categories. Nuclear pasta is neither a normal solid nor a normal liquid. It is a phase of matter where the nuclear material itself has been molded into extended geometric structures, strands and sheets and tubes and bubbles, on scales unimaginably tiny, yet shaped by the same kind of balance between competing forces that, on enormous scales, shape soap bubbles and foams. Recent computer simulations and theoretical work suggest that nuclear pasta may be among the strongest materials in existence, even stronger than the crystalline crust above it. Because to deform these interlocking sheets and tubes, you would have to overcome the full might of the strong nuclear force arranged across extended structures. The matter has crushed itself into a new architecture, and in doing so it has become tougher than anything we could ever forge. And the pasta is not merely a curiosity of exotic geometry, it may set limits on what neutron stars can do. Because this layer is so strong and so resistant to deformation, it may determine how large a bump the star can sustain, and therefore how much the star can radiate away its rotational energy in gravitational waves. It may also influence how electrical currents and heat flow through the deep crust, which in turn shapes how the star cools and how its magnetic field evolves over millions of years. So this strange layer, named after dinner, is woven into some of the most important long-term behaviors of the entire object, a reminder that even the most whimsically named physics can have serious consequences. Now we pass beneath the crust, beneath the pasta, and we enter the core, and here the matter becomes uniform again, but it is a uniformity of a profoundly strange kind. We have arrived at the bulk neutron matter we described earlier. The ocean of free neutrons with its small admixture of protons and electrons, all packed to nuclear density and beyond. But describing this matter as merely an ocean of neutrons badly undersells what is actually going on, because this neutron ocean is not an ordinary liquid at all. It is something far more exotic. The neutrons in the outer core are believed to form a superfluid, and the protons are believed to form a superconductor. And to understand what those words mean is to understand some of the most counterintuitive behavior matter is capable of anywhere in the cosmos. Let's take the superfluid first. A superfluid is a liquid that flows with absolutely no friction, no viscosity whatsoever. This is not merely a liquid that flows easily, it is a liquid that flows with literally zero resistance, a perfect, frictionless fluid. On Earth, we can create superfluids only under the most extreme conditions, cooling certain substances like helium to within a hair's breadth of absolute zero, the coldest temperature physically possible. When helium becomes a superfluid in a laboratory, it does things that seem to violate common sense. It will climb up the walls of its container and flow over the top. It will pass through cracks so tiny that no ordinary liquid could penetrate them. It will, once set spinning, continue to spin essentially forever, because there is no friction to slow it down. Superfluidity is a quantum phenomenon, a state in which a vast number of particles fall into the same coordinated quantum state and behave as a single, unified entity rather than a jostling crowd of individuals. Now, here is what is astonishing about a neutron star. The interior of a neutron star is extremely hot by everyday standards, hundreds of thousands or even millions of degrees, and yet the neutrons in the core can still form a superfluid despite that heat. How? Because the relevant comparison is not to room temperature but to the fantastically high energies involved in nuclear matter. The neutrons are packed so densely and bound so strongly that the temperature, high as it is in absolute terms, is effectively cold relative to the energy scales of the nuclear interactions. So the neutrons pair up and fall into a coordinated quantum state, and the bulk of the neutron star's interior becomes a frictionless superfluid, an ocean the size of a city that flows without any resistance at all. And the protons, similarly paired, become a superconductor, which is the electrical analog of a superfluid, a state in which electrical current flows with zero resistance and magnetic fields behave in strange, organized ways. So, the core of a neutron star is remarkably both the densest known form of matter and simultaneously the largest superfluid and superconductor in the universe. It is worth noting that the superfluidity is not all of one kind either. In the inner crust, where free neutrons flow among the lattice nuclei, the neutrons pair up in one particular way, while deeper in the core, where the density is far higher, they pair up in a different way altogether, because the nature of the force between neutrons changes with density. This means a neutron star may contain not one superfluid, but several distinct superfluid regions, each with its own character layered within one another. Tracking how these different superfluids cool and how they couple to the crust and the magnetic field is one of the ways physicists test their models against the slow, decades-long temperature changes we can actually observe in some neutron stars as they gradually radiate their birth heat into space. This is not just a curiosity, it has observable consequences, and this is one of the most satisfying parts of the whole story, because it connects the abstract, exotic physics of the deep interior to something we can actually measure from across the galaxy. Recall that neutron stars spin, often very rapidly, and that we detect many of them as pulsars, those cosmic lighthouses flashing with extraordinary regularity. The spin of a pulsar is one of the most precisely measurable quantities in all of astronomy. We can track the rotation of some pulsars so accurately that they rival atomic clocks, and over time, a pulsar's spin gradually slows down, very slightly, as it radiates energy away. This slowing is smooth and predictable year after year, decade after decade, but every so often, in certain pulsars, something abrupt happens. The spin rate suddenly jumps. The star momentarily spins a tiny bit faster, in defiance of the steady slowing. These sudden spin-ups are called glitches, and for a long time they were mysterious. What could possibly make a slowing star suddenly speed up? The leading explanation involves precisely the superfluid we have been discussing, and it is a wonderful piece of physics. The superfluid neutrons in the interior do not slow down in lockstep with the solid crust. Because they are frictionless, they keep spinning at their own rate, storing rotational momentum. A spinning superfluid arranges itself into a vast array of tiny whirlpools called vortices, and these vortices can become pinned, snagged against the structures in the crust, including potentially the nuclear pasta. As the crust slows but the superfluid keeps spinning, a difference builds up between them, a kind of rotational stress. Eventually that stress reaches a breaking point. The vortices suddenly unpin all at once, and the superfluid dumps a burst of its stored rotational momentum into the crust, spinning the whole star up by a tiny but measurable amount. That is the glitch. Think about what this means. We are detecting, from thousands of light years away, the signature of a frictionless quantum superfluid, sloshing inside the densest matter in the universe. A sudden hiccup in the timing of a pulse, observed by a radio telescope on Earth, is a direct fingerprint of vortices unpinning in an ocean of superfluid neutrons buried beneath the crust of a collapsed star. The exotic interior is not merely theoretical speculation, it leaves traces we can see. This is what makes these objects so valuable to physics. The most extreme matter in the cosmos hides where no instrument could ever touch it, and yet it still betrays itself, echoing outward into properties we can measure. The spin, the radiation, the timing of the pulses, giving us a handle on states of matter that would otherwise stay forever hidden. Let me also address the magnetic dimension of this layered world, because it weaves through everything. We mentioned that neutron stars possess the strongest magnetic fields known anywhere, and that the most extreme of them, the magnetars, have fields of almost incomprehensible strength. These fields are not confined to the surface, they thread through the entire star, from the superconducting core, through the crust and pasta, out into the thin atmosphere and beyond. In the superconducting core, the magnetic field is believed to be organized into tight bundles, concentrated into thin tubes of magnetic flux that thread the proton superconductor. The interplay between the spinning superfluid, the magnetic flux tubes, and the rigid crust creates a coupled, dynamic system of staggering complexity. A system in which the deepest, most exotic physics is constantly interacting with the structure of the layers above. In the case of magnetars, the fields are so intense that they can stress and crack the incredibly strong crust, producing sudden, violent releases of energy. A single such event, lasting only a fraction of a second, can release more energy than the sun emits in many thousands of years. And these starquakes have been detected as bursts of high-energy radiation sweeping across the galaxy. And one of these events gives us perhaps the most startling demonstration of just how far the reach of a neutron star extends. In late 2004, a magnetar on the far side of our galaxy, a member of the class astronomers called soft gamma repeaters, an object designated by the letters SGR and a string of numbers, unleashed a single titanic flare. For a fraction of a second, this one starquake outshone the entire rest of the galaxy in high-energy radiation. The burst had crossed tens of thousands of light years of space, and when it arrived at Earth, it was still powerful enough to measurably disturb the upper layers of our atmosphere, the ionosphere, the same region that affects radio communications. Think about that. A crack in the crust of a dead star on the opposite side of the Milky Way reached across an almost unimaginable gulf of space and physically nudged the atmosphere of our own planet. It is one of the most vivid reminders that these objects, however remote and however strange, are not sealed away in their own separate universe. The crushed matter we have been describing produces forces so extreme that their echoes can touch us directly, even from across the galaxy. So let us assemble the full picture of the layered world we have descended through. At the top, a wisp of an atmosphere, a few centimeters of crushed plasma, shaping the light we ultimately detect. Beneath it, the outer crust, a crystalline lattice of iron and heavier nuclei, threaded by a sea of free electrons. A material billions of times stronger than steel, polished by gravity into near-perfect smoothness, with mountains no taller than a fingernail. Deeper, past the neutron drip threshold, the inner crust, where free neutrons flow between the lattice nuclei, a solid and a liquid intertwined. Then the pasta layers, where the contest between the strong force and electrical repulsion molds nuclear matter into blobs, strands, sheets, and their inversions, an architecture of the very strong force itself, possibly the toughest material in existence. And beneath all of that, the core, the vast superfluid ocean of neutrons, the superconducting protons, the organized magnetic flux, a frictionless quantum sea the size of a city, whose internal motions we can read in the glitches of distant pulsars. It is worth stepping back to appreciate the sheer dynamic range of this object. From the surface to the center, we have descended only perhaps 10 or 15 kilometers, a distance you could walk in a couple of hours on Earth. And yet, across that tiny span, the density has climbed by a factor of millions, and the matter has passed through more distinct and exotic states than we encounter across the entire rest of the universe. We have gone from crushed plasma to the strongest crystal in existence, to a fluid that flows with no friction in the span of a few kilometers. Nowhere else in nature is so much variety of matter compressed into so small a space. A neutron star is, in this sense, an entire physics curriculum compressed into a sphere the size of a city. Condensed matter physics, nuclear physics, the physics of superfluids and superconductors, the physics of magnetism, all stacked one atop another and all pushed to extremes we cannot reach by any other means. And throughout this entire descent, notice how thoroughly the matter has departed from anything we would recognize. There is not a single atom anywhere in this structure in the ordinary sense. There is no chemistry, no molecules, no elements behaving as they do on Earth. The very nuclei have been transmuted into neutron-saturated forms impossible in any laboratory. And in the pasta layers, they have abandoned the spherical shape that nuclei have held throughout the rest of the cosmos. The matter that holds the star up is a frictionless quantum fluid of particles that would be unstable if you set even one of them free. Every layer is a fresh demonstration of the title's promise. Ordinary matter crushed past the point where its familiar structures can survive, and forced into states that exist nowhere else. Yet, for all the strangeness we have catalogued, we have still been describing matter in terms of neutrons and protons, the same particles that make up ordinary nuclei, merely rearranged and compressed and made to do exotic things. We have crushed the atoms, transmuted the nuclei, and force the neutrons into superfluid order. But the fundamental cast of characters, neutrons, protons, electrons, has remained the same throughout. And this brings us to the deepest question of all, the one waiting for us at the very center of the star. Because as we descend into the inner core, the density climbs higher still, beyond even the density of an ordinary atomic nucleus, into a regime where our confident knowledge begins to run out. At those densities, there is reason to believe that even the neutron itself, the particle on which this entire object is built, may no longer be able to hold itself together. The very description of matter as neutrons and protons may begin to break down, and something far more exotic, something that pushes the meaning of the word matter to its absolute limit, may take its place. That deepest frontier where the building blocks themselves may dissolve is where our descent must finally take us. We have descended through the atmosphere, the crust, the pasta, and into the superfluid ocean of the outer core. Now we make the final descent into the deep core, the very center of the neutron star. And here we arrive at the true frontier of physics, the place where our confident knowledge runs out and the most extraordinary possibilities open up. Because everything we have described so far, strange as it has been, has still been built from particles we know: neutrons, protons, and electrons. The matter has been crushed, transmuted, rearranged into superfluids and pasta, but the fundamental cast of characters has remained familiar. In the deep core, that may no longer be true. Here, at densities exceeding even the density of an ordinary atomic nucleus, there is reason to believe that the neutrons themselves, the very particles on which this entire object is built, may begin to dissolve. And to understand how that could happen, we need to look inside the neutron itself. A neutron, it turns out, is not a fundamental, indivisible particle. It has internal structure. Each neutron is made of 3 smaller particles called quarks, bound together by an extraordinarily powerful force called the strong force, which is carried by particles called gluons. Specifically, a neutron is made of 1 up quark and 2 down quarks, while a proton is made of 2 up quarks and 1 down quark. These quarks are confined inside the neutron or proton, held together so tightly that, under all ordinary circumstances, they can never escape. This property is called confinement, and it is one of the deepest features of the strong force. You cannot pull a single quark out of a neutron. If you try, the force between the quarks does not weaken with distance the way gravity or electricity does. Instead, it grows stronger, so that pulling harder simply stores more and more energy until that energy becomes great enough to create new quarks out of empty space, which immediately pair up to form new particles. The result is that quarks are always locked away inside larger particles, never seen in isolation. For all of ordinary physics, the quarks inside a neutron might as well be sealed in a vault. But the deep core of a neutron star is not ordinary physics. As we descend toward the center, the neutrons are packed more and more tightly together, until they are essentially touching, until they are squeezed so hard that they begin to overlap. And here is the profound question that physicists have wrestled with for decades. What happens when you squeeze neutrons so tightly that there is no longer any clear space between them, when their boundaries blur and they begin to merge into one another? At some critical density, it may no longer make sense to talk about individual neutrons at all. The quarks that were confined inside each separate neutron may find themselves no longer confined to any particular neutron, free instead to roam throughout the bulk of the matter. the walls of the vaults dissolve and the quarks spill out, not into empty space, where confinement would forbid them, but into a shared sea where they are all packed together so densely that the usual rules of confinement no longer apply in the same way. This is called deconfinement, and the resulting substance is called quark matter, or quark-gluon plasma. Let me make sure the magnitude of this idea is clear, because it is the ultimate fulfillment of the title's promise. Throughout this entire story, we have watched matter crushed out of one form after another. First, the atoms were crushed, their electron clouds stripped away. Then the nuclei were transmuted, their protons converted to neutrons. Then even the neutrons that dripped free were forced into exotic superfluid order. But in every case, the matter was still made of recognizable particles. Now, in the deep core, we're contemplating the possibility that the particles themselves, the neutrons and protons that have been the bedrock of everything, are crushed out of existence too, dissolved into their constituent quarks. This would be matter in its most fundamental, most deconstructed form. Not atoms, not nuclei, not even neutrons, but a sea of free quarks and gluons, the very building blocks of matter laid bare and flowing freely. If this happens at the center of neutron stars, then those centers contain the most extreme state of matter that can exist anywhere in the present universe, a state that otherwise existed naturally only in the first fleeting microseconds after the Big Bang, when the entire cosmos was hot and dense enough to be a quark-gluon plasma. And there is a further twist that makes this deconfined matter even stranger. The quarks, like the neutrons and electrons before them, obey the exclusion principle, and so they too may pair up and fall into coordinated quantum states, just as the neutrons did to form a superfluid. But quarks carry a property that physicists, with their gift for vivid naming, call color, which is the kind of charge associated with a strong force, nothing to do with visible color at all. When quarks pair up in the deep core, they may form a state called a color superconductor, a phase in which the strong force equivalent of electric current flows without resistance. This would be a superconductor not of ordinary electric charge, but of the strong force itself, and it could come in several distinct varieties depending on exactly how the up, down, and strange quarks pair with one another. So the very center of a neutron star may be not just a sea of free quarks, but a color superconductor, an exotic phase of matter that has no analog anywhere in our experience, and that exists, if it exists at all, only in the hearts of these collapsed stars. We have gone from crushing atoms to a frictionless ocean of neutrons, all the way down to a frictionless ocean of the deconfined building blocks of neutrons. The layering of exotic physics and simply does not stop. Now, I have to be honest with you about the state of our knowledge here, because honesty is part of what makes this frontier so compelling. We do not know for certain that quark matter exists in the cores of neutron stars. This is a genuine open question at the cutting edge of physics, and it is open for a fundamental reason. The physics of matter at these densities is extraordinarily difficult to calculate. The strong force which governs how quarks and neutrons behave is mathematically ferocious. It is relatively tractable at very high energies, where a strange feature called asymptotic freedom causes the force between quarks to weaken. But at the densities and energies relevant to neutron star cores, the force is in its most intractable regime. And our most powerful computational techniques struggle to give definitive answers. We cannot simply solve the equations and read off whether the core is made of neutrons or quarks. So physicists must work with a range of theoretical models, each making different assumptions, and then compare their predictions against the observations we can make of real neutron stars. The question of what lies at the center is being actively decided right now by the interplay of theory and observation, and it is one of the most exciting frontiers in all of physical science. What are the candidates then for what the deep core might contain? Let's survey them, moving from the more conservative to the more exotic, because the range of possibilities is itself a vivid illustration of how far beyond familiar matter we have traveled. The most conservative possibility is that the core remains made of neutrons and protons all the way down, with no dramatic transformation, just neutron matter compressed to ever higher densities. Even this conservative picture involves matter far denser than an atomic nucleus, behaving in ways we cannot fully calculate, but at least the particles remain familiar. This is the baseline against which the more exotic possibilities are measured. A step beyond that is the possibility of new particles appearing. Particles that are cousins of the neutron and proton but heavier and stranger. The neutron and proton belong to a family of particles called baryons, all made of 3 quarks. The neutron and proton are the lightest members of that family, which is why they are the ones that make up ordinary matter. Nature prefers the lightest option when it can. But under the crushing pressure of a neutron star core, that preference can change. Recall the logic we used again and again earlier in this story. The exclusion principle forces particles into ever higher energy states as they are packed tighter. The neutrons at the top of their degeneracy carry enormous energies, and at some point it can become energetically cheaper to create a heavier particle than to force yet another neutron into an even higher energy state. When that threshold is crossed, the matter begins to convert some of its neutrons into these heavier cousins. The most discussed of these heavier cousins are the hyperons, baryons that contain at least one strange quark, a heavier relative of the up and down quarks that make up ordinary neutrons and protons. On Earth, hyperons are fleeting, exotic things, created momentarily in particle accelerators and decaying almost instantly. Because they are heavier than neutrons and nature lets them tumble back down to lighter particles. But in the core of a neutron star, the same exclusion principle trap that stabilized free neutrons can stabilize hyperons too. With the lower energy states all filled by neutrons, a hyperon, despite being heavier, can actually represent a lower energy way to add another particle to the mix, and its decay back to a neutron is blocked because there is no available state for the neutron to occupy. So the deep core may contain a population of these strange, heavy baryons, particles that cannot survive for more than an instant on Earth, but which may exist stably and in bulk inside neutron stars. The matter would then be not just neutron matter, but a richer brew of baryons, including these strange particles, a kind of zoo of exotic matter assembled by the crushing pressure. There is a further possibility along similar lines, involving particles called mesons. Mesons are another category of particle made from quarks, but where baryons are made of 3 quarks, mesons are made of a quark and an antiquark. Certain mesons, particularly ones called kaons and pions, might, under the extreme conditions of the core, undergo a process called condensation, in which a large number of them fall into the same lowest energy quantum state, forming what is called a meson condensate. This is conceptually related to the superfluid behavior we discussed earlier. a great many particles coordinating into a single shared quantum state. But here it would be a state filled with these exotic mesons. A kaon condensate or a pion condensate in the core would soften the matter, change how it resists compression, and alter the structure of the star in ways that, again, might leave observable fingerprints. Whether such condensates actually form is, like so much else at this frontier, an open question. And then there is the most dramatic possibility of all: full deconfinement into quark matter, the dissolution of the neutrons and protons into a sea of free quarks that we described a moment ago. In this picture, the very center of the star is no longer made of distinct particles at all, but of up, down, and strange quarks, all flowing together in a single deconfined sea, bound not into individual neutrons, but into the bulk matter as a whole. A neutron star with such a core is sometimes called a hybrid star, because it would have an outer region of ordinary neutron matter surrounding an inner core of quark matter, the two separated by a transition region where the neutrons gradually dissolve. The boundary between the neutron matter and the quark matter would be a kind of frontier within the star, a surface where the fundamental nature of matter itself changes from confined to deconfined. But there is an even more radical idea waiting at the end of this road, and it is one of the most provocative hypotheses in all of physics. It is the idea of a strange matter and the possibility of strange stars. Here is the reasoning, and it is genuinely startling. We normally assume that ordinary nuclear matter made of neutrons and protons is the most stable form that bulk matter can take. That assumption underlies everything, including our confidence that the world around us will not suddenly transform into something else. But some physicists have proposed that this assumption might be wrong. They have suggested that the truly most stable form of bulk matter might not be ordinary nuclear matter at all, but a particular kind of quark matter containing roughly equal numbers of up, down, and strange quarks, a substance called strange quark matter. The idea is that because the strange quark provides an additional type of particle for the quarks to occupy, the exclusion principle can be satisfied at a lower total energy, making strange matter potentially more stable, more tightly bound than ordinary matter. If this hypothesis is correct, the implications are extraordinary. It would mean that ordinary matter, the matter you and I and the entire Earth are made of, is not truly stable, but merely long-lived. A metastable state that has simply never had the opportunity to convert into the lower energy strange matter. The reason ordinary matter does not spontaneously transform is that converting it would require simultaneously transforming a great many quarks at once, a process so improbable under normal conditions that it essentially never happens, even over the entire age of the universe. But inside a neutron star core where quarks may already be deconfined, the conditions might exist for a seed of strange matter to form, and once formed, that seed could potentially convert the surrounding neutron matter into strange matter, growing as it goes. The entire star might, in this scenario, convert from a neutron star into a strange star, an object made not of neutrons at all, but of bulk, strange quark matter, held together not just by gravity, but by the strong force acting across the whole object. Such strange stars would have subtly different properties from ordinary neutron stars. Different relationships between their mass and their size, different surface structure, potentially even a sharp, bare quark matter surface rather than the crust and atmosphere we described. Astronomers actively look for these differences, trying to determine whether any of the compact objects we observe might be strange stars rather than ordinary neutron stars. And there is a small, lingering chunk of strange matter in this hypothesis that has occasionally caused alarm. A small piece of strange matter called a strangelet. If it existed, and if the hypothesis were true, could in principle convert ordinary matter it touched. This has led to occasional worries, but it is worth being clear and reassuring here. Cosmic rays of enormous energy have been striking the Earth, the Moon, and everything else for billions of years. And if dangerous self-propagating strangelets were easily produced, or easily able to convert ordinary matter, the universe would look very different than it does. The continued existence of ordinary matter, the Moon, the planets, ourselves, across billions of years, is itself strong evidence that whatever strange matter may or may not be, it does not pose the kind of runaway threat that the most fevered speculation imagined. It remains a fascinating theoretical possibility about the deep interiors of collapsed stars, not a danger lurking in everyday life. So how do we possibly hope to resolve all of this? How do we determine what actually lies at the center of a neutron star, in a region buried beneath kilometers of the strongest, densest material in the universe, an interior we can never directly see or sample? This is where the story becomes wonderfully concrete again, because nature has given us a remarkable lever for prying open these secrets, and it comes down to a single principle. The internal composition of a neutron star determines how the matter resists compression, and that resistance determines the relationship between the star's mass and its size. Different kinds of matter, neutron matter, hyperon matter, quark matter, strange matter, each resist compression differently. Stiffer matter resists more and produces larger stars for a given mass and supports more total mass before collapsing. Softer matter resists less and produces smaller, more compact stars and collapses at lower masses. So if we can measure the masses and the sizes of real neutron stars precisely enough, we can work backward to constrain what they are made of. The matter at the center writes its signature into the overall dimensions and mass limit of the star, and we can read that signature from afar. This is why one particular kind of observation has been so revolutionary. There is an absolute upper limit to how much mass a neutron star can have, an analogue to the Chandrasekhar limit we met at the very beginning of this story, but for neutron stars rather than white dwarfs. It is called the Tolman-Oppenheimer-Volkoff limit, the TOV limit, and it represents the maximum mass that neutron degeneracy pressure and the strong force can support before gravity wins and the object collapses all the way into a black hole. The exact value of this limit depends on what the matter is made of, on how stiff or soft it is at the highest densities. So every time astronomers discover a neutron star that is especially massive, it places a powerful constraint on the physics of the interior. If a neutron star is found with around 2 times the mass of the Sun or more, then whatever its core is made of must be stiff enough to support that much mass. And this rules out the softest models, including some versions of hyperon matter and some versions of quark matter that would have collapsed before reaching such a mass. The discovery of these heavy neutron stars, several of them now confirmed at roughly 2 solar masses, has therefore been enormously informative, narrowing down the possibilities and forcing theorists to refine their models of what the deep interior can and cannot be. The measurement of size has proven even harder than the measurement of mass, but here too, there has been a genuine revolution, and it has a name worth knowing. A space-based instrument called NICER, mounted on the outside of the orbiting space station, was built to do something exquisitely delicate: to watch the X-ray light from hotspots on the surfaces of spinning neutron stars and measure with extraordinary precision how the timing and brightness of that light is shaped by the star's own gravity. Because a neutron star's gravity is so intense, it bends the light leaving the surface so that we can actually see slightly around the far side of the star. And the way the hotspots appear to brighten and fade as the star rotates encodes the ratio of its mass to its radius. By carefully modeling that pattern, physicists have begun for the first time to pin down the actual sizes of specific neutron stars to within a kilometer or two. Combine those size measurements with the mass measurements, and you begin to map out the relationship between mass and radius for real objects. And that map is precisely what distinguishes one model of the interior from another. We are, in effect, weighing and measuring objects thousands of light years away in order to deduce what the matter at their unreachable centers is made of. And then, there is an even more spectacular source of information, one that opened up only very recently in the history of science: gravitational waves. When two neutron stars orbit each other and finally spiral together and merge, the cataclysm sends ripples through the fabric of space-time itself. Ripples that we have now learned to detect with extraordinary instruments here on Earth. In the final moments before two neutron stars collide, they orbit so closely and so fast that the gravity of each one raises enormous tides on the other, deforming it, stretching it out of its spherical shape. How much a neutron star deforms under such tidal stress depends once again on what it is made of. Stiffer matter deforms less, softer matter deforms more. And remarkably, that deformation leaves an imprint on the gravitational waves the merger produces. By analyzing the precise shape of the gravitational wave signal from a neutron star merger, physicists can measure how deformable the stars were, and from that, constrain the stiffness of the matter, and from that, constrain its composition. We are quite literally reading the internal physics of neutron stars in the ripples they send across space-time as they die. The first such detection of a neutron star merger, observed in both gravitational waves and light, was a landmark moment, and the events detected since have steadily tightened the constraints on what neutron star matter can be. Combined with the mass measurements and the nicer size measurements, we are slowly, painstakingly closing in on an answer to the question of what lies at the center. We are not there yet. And here we run into one of the most frustrating and fascinating obstacles of all, a problem physicists have nicknamed the masquerade. It turns out that a neutron star with a quark matter core can, in many cases, look almost exactly like a neutron star made entirely of ordinary neutron matter, with nearly the same mass, nearly the same size, nearly the same deformability. The quark core, in other words, can wear the mask of ordinary matter, hiding its true nature behind observable properties that barely differ. This is why confirming the presence of deconfined quark matter has been so stubbornly difficult. The data so far is consistent with several possibilities and has not definitively revealed a quark core, nor ruled one out. Distinguishing the masquerade may require not a single measurement but the patient accumulation of many across many objects, slowly tightening the net until only one explanation survives. But the trajectory is clear. We are turning a question that was once pure speculation into a question that can be answered by measurement, and that transformation from speculation to science is one of the great achievements of modern physics. Let us now stand back and take in the entire journey we have made, because it tells a single, unified story. We began with a massive star, locked in the long stalemate between fusion and gravity. When its fuel ran out and its iron core grew past the Chandrasekhar limit, gravity won, and the collapse began. In a fraction of a second, gravity crushed the atoms out of existence, stripping electrons from nuclei and dissolving the very structure that defines ordinary matter. That vast internal emptiness wrung out entirely. Then gravity reached deeper, forcing electrons into protons, transmuting them into neutrons, neutralizing the matter, and consuming the very particles that had been holding the collapse at bay. The neutrons that resulted, unstable in isolation, were rendered stable in bulk by their own crushing density, and their quantum stubbornness, their degeneracy pressure, became the new pillar holding up the star. We descended through the layered world that this crushing built, the wisp of atmosphere, the crystalline crust stronger than steel, the bizarre geometry of nuclear pasta, the frictionless, superfluid ocean whose hidden motions we read in the glitches of distant pulsars. And finally, at the deepest center, we reach the ultimate frontier, where even the neutrons may dissolve, where the quarks confined within them may spill free into a deconfined, color superconducting sea, where matter may take on its most fundamental and most exotic form, perhaps even the strange matter that some believe could be more stable than the ordinary matter we are made of. At every step, the same theme has recurred. Gravity, given enough mass concentrated in a small enough space, is capable of crushing matter across one threshold after another, dismantling its structures from the largest down to the smallest. The atom falls first, then the nucleus is rewritten, then the neutron itself may come undone. Each threshold is a place where some structure that ordinary matter relies upon simply cannot survive, and the matter is forced into a state more extreme, more alien, more removed from anything in our experience. This is what it truly means to crush matter out of existence, not to destroy it utterly, for the energy and the constituents remain, but to obliterate, one layer at a time, every familiar form that matter can take, until what remains bears no resemblance to the matter we know, until the very words we use, atom, element, particle, begin to lose their meaning. And there is a final thought worth holding on to, one that brings this cosmic extremity back to ourselves. The atoms in your body, the calcium in your bones, the iron in your blood, were forged inside stars and scattered across space by the supernova explosions that accompany the very collapses we have been describing. Every neutron star that exists was born in an explosion that seeded the galaxy with the raw material of future worlds and future life. And we now have direct evidence that many of the heaviest elements, very likely including much of the gold and the platinum in existence, are forged in the violent collisions of neutron stars themselves, flung out into space when these crushed remnants tear each other apart. So these objects, where matter is crushed beyond all recognition, are not merely distant curiosities. They are part of the same grand cycle that made us. The same crushing gravity that destroys atoms in a stellar core is part of the process that, in the explosion surrounding that core, creates and disperses the atoms that eventually become planets and oceans and living things. We are, in the most literal sense, the products of the deaths of stars. And when we study the crushed hearts those deaths leave behind, we are studying the most extreme expression of the very forces that brought us into being. To understand a neutron star is to understand just how far matter can be pushed, and in that understanding, to glimpse both the violence and the strange, intricate beauty of the universe that made us.